For day 10, we are now going to be using row-reduced echelon form to solve systems. So I've started off here with two problems, both that are the exact same, but we're going to use two different methods to solve them. For the first system, I want to solve this algebraically. So I take a look at this, and I think the easiest way probably is just to multiply by 2 to try to eliminate the x's. And I get 6x minus 4y equals 12. Now, when I add these two lines together, I get 0 equals 20, which we know is a false statement. And because it's false, we say this is no solution because these lines are parallel. Now, I'm going to also do the same exact system here using inverse matrices, what we did yesterday using our calculator. So I went ahead already and I put that into my calculator. So in my calculator, I have matrix A listed as 3, -2, -6, and 4, and matrix B is listed as 6 and 8. Okay, those are that's my constant matrix and my coefficient matrix. So when I come to my calculator and I enter A inverse B, I'm going to get this weird error message. Okay, so it says error singular matrix. So I have no idea what the answer to this is because I get this strange error. So we get an error message when we use inverse matrices. That's why today we're going to use something different using our calculator. We're going to use row-reduced echelon form. Okay, row-reduced echelon form. So instead of entering our matrix as two separate matrices, we actually are going to enter one matrix. So we take this matrix, this is again the same exact problem, and we're going to let A now equal a 3 by 2 matrix, and we're going to put everything in here except for the variables. So we write this as 3, -2, 6, and -6, 4, 8. Okay, we go into our calculator and we enter that. Okay, sorry about that. It's actually, I messed it up. It's a 2 by 3. I drew it correctly and then I named the dimensions wrong. But anyways, here you can see that I already edited the matrix here to reflect this new 2 by 3 matrix. So now in my calculator, instead of hitting A and doing A inverse times some other matrix, I'm going to scroll over to math. So scroll to the right. You're going to scroll down till you see RREF. Ref. Okay, so don't hit the first one, REF. You want to do row reduced echelon form. So hit B, and whoops, sorry, I forgot to quit out of there. Let's do that one more time. So second matrix, scroll over to math, scroll down to ref. Where are you? Oh, went too far. And now enter matrix A. Hit enter, and that's going to spit out your answer. Now I'm going to, since I see this decimal here, I'm going to hit math, enter, enter to convert that to a fraction. And so I get this nice matrix here, and it says that I have row reduced echelon form of this matrix. Matrix A is 1, -2/3, 0, 0, 0, 1. Okay, so let's talk about what this means. When I look at this, this is giving me x, y equal to 0. So I have 1x minus 2/3 y equals 0, and I have this bottom statement here that says 0x plus 0y equals 1. In other words, 0 equals 1, which we know to be false, which is why this system has no solution. So row-reduced echelon form allows us to actually figure out what the solution to this system is, whereas before, with inverse matrices, we just get that error message. So that's why we no longer want to use just inverse matrices. Some of you might be more comfortable with using inverse matrices. You might really like this, but I think you're going to like row-reduced echelon form because you only have to fill out one matrix. And again, all you do is say let A equal, now you include all of the coefficients and the constant matrix together. You hit row-reduced echelon form and it spits out an answer. So let's just practice this again, just so you get the hang of it. In problem number 4 here, if I let A equal 11, -5, -38, and 9, 2, -25, in my calculator, and on paper I want to write RREF, but that's all I need to enter into my calculator. So I'm going to edit that real quick in my calculator, and you can do the same, just pause. Okay, so here you can see I edited matrix A, okay, to reflect our new matrix, and I'm going to quit out of here. And instead of having to hit, RREF A again, I'm going to hit second entry and use that shortcut that I showed you guys. But this is the last thing I entered, so I want to hit second entry one more time, and it calls up the last thing. So if you keep hitting second entry, second entry, second entry, it keeps running through all the things that you entered into your calculator. So I think that's kind of a nice function of the calculator. So anyway, I hit enter, and I have this matrix here, 1, 0, 0, 1, negative 3, 1. Okay, so let's interpret it in this matrix. Now, these two columns here were my x and y. So I have 1x plus 0y equals negative 3, and I have 0x plus 1y equals 1. Well, what this is saying, if you ignore that 0y, x just equals negative 3, and here if I ignore the 0x, y equals 1. So when you read your row-reduced echelon form of your matrix, these represent your solutions with x and y here. Okay, so it's pretty quick and really easy to solve the system now. Let's work on matrix, or number 5. So let's let matrix A now equal 8, negative 12, 24, 6, negative 9, and 18. So let's go ahead and enter that into our calculator. Okay, here I want to show you that I did edit the matrix, and I want to show you another thing that you can just double check to see if you have the correct matrix shown, because sometimes you're going to get frustrated and you'll be like, well, how come I'm not getting the same answer that you're getting on the video? It might be because you entered something incorrectly, so always double check that you have your matrix shown as the same thing that you wrote down. So if I hit second matrix and just hit enter on A, if I hit enter here, it's going to show me what I have entered for each cell in matrix A. So I do have it switched to 8, negative 12, 24, 6, negative 9, and 18. So again, this is just one way for you to double check that you have the correct things inside your matrix. So let's do row-reduced echelon form of matrix A. So second matrix, scroll over to math, and then down to RREF. This takes my calculator a long time because it's a little slower than yours. Yours should go much quicker than mine. Hit enter on RREF, second matrix A, and hit enter, and I get 1, negative 1/2, 3, and then 0, 0, 0. Alright, now if I interpret this one, it's going to be slightly different than our last matrix before this. Okay, so notice how I'm labeling this too. I have A, and then I rate RREF of A so that I don't confuse the two, and then also when I'm grading I can tell what you're trying to write. But when I want to interpret the solution, I can get rid of the calculator right now. Okay, so looking at the solution here, this is saying in the first line x minus 3 halves y, or negative 1.5 y, it doesn't matter, I just changed it to a fraction, is equal to 3. And then on the bottom it says 0x plus 0y equals 0. Well, I basically get the statement 0 equals 0. We know that whenever we get the statement that says 0 equals 0, or a true statement, that this has an infinite number of solutions. So this is actually the line, the linear system, or the line of the equation that all the points are on. So this is infinite solutions for all points on the line x minus 3 halves y equals 3. Okay? And you could also use any of these two lines as well, because those are all equivalent to x minus 3 halves y equals 3. But that's how you would read this each solution. So now on the back page here, I have 4 different problems where you're interpreting the solution. So I would like you guys to try to pause the video at this point, do these questions on your own, and check with the key. I am going to go through the solutions, but I want you to try these out first, just to make sure that you actually can do this before we move on to our word problem. Alright, in problem number 1, 1x plus 0y equals 3, so in other words, x equals 3, and y equals negative 4, because 0x plus 1y equals negative 4. In number 7, this is a true statement in the bottom. We have 0 equals 0, which means that this is all points on the line, x minus 2y equals 3. So it's all points on this line here. In problem number 8, this in the bottom is false. 0 does not equal 1, so this has no solution because our lines are parallel. So it's very similar to what we did in problem number, I guess, 1, the first 3 questions that were all the exact same. In problem 9, you might notice now that you have actually a bigger matrix. This is a 3 by 4 matrix, okay, and inside here, hopefully you're recognizing this as the identity matrix. You have the identity matrix here, and you've got 3 different variables this time. This represents an x, y, and a z. So this time you have x equals 2, y equals 3, and z equals 4. You can write this as the order triple 2, 3, 4. Okay, so that's a 3 variable system there, which is why it's really nice to use our calculators, because now we can shorten up all that work that we used to do algebraically just by using our calculator. Alright, now let's work on a word problem. You will be doing 3 variable and 2 variable word problems. So what's nice is you now have a calculator, so you can check your answers. If you have to do it algebraically, you can always check your answers. Or most of the time, we're going to let you use your calculator to solve a system that's in 3 variables now. So it's kind of nice, because you don't have to, worry through all those, those little negative signs that you would make mistakes on before. Okay, anyhow, I'm rambling. In number 10, it says the number of cents per mile it costs to drive a car depends on how fast you drive it. So at low speeds, the cost is high because the engine is operating inefficiently. And then at high speeds, the cost is also high because the engine must overcome high wind resistance. When you're at moderate speeds, the cost reaches a minimum. So, if somebody drives their car like a maniac at high speeds, they're usually burning a lot of gas. If you drive super slow, same thing. You're costing a lot of gas. But your gas mileage is actually best when you're driving at moderate speeds, like, I don't know, anywhere from like 40 to 60 miles per hour. My car, as soon as I go like 65, it starts really guzzling a ton of gas. So kind of stinks when you're doing highway driving. You can't go over 65. But anyhow, it tells you in this question that the cost varies quadratically with the speed of the car. So we're not using a linear model in this case. We're using a quadratic model. And a quadratic, we kind of briefly studied this a little bit. The next chapter we're going to study this a whole lot, because it's all about quadratics. But this is a general quadratic equation. This would be a linear equation, mx plus b. This is y equals ax squared plus bx plus c. This is a quadratic equation. So our graph of this would actually be a parabola. Now, they tell us, and they relate the variables for us. They say that cost is equal to a constant, times your speed squared, plus b, a constant, times your speed, plus c, another constant. So we've got another set of data here that says, suppose that at a speed of 10, 20, and 30 miles per hour, the cost is 28, 21, and 16 cents per mile. So it asks, what are the 3 ordered pairs? The first thing I want to do is define my variables. Notice how this is ax squared. So x here is my speed, and y equals cost. You can kind of also tell that based off of our beginning sentence here when it says cost varies with speed. Remember how y varies with x when it's linear? It's the same thing for quadratically. So we've got y is our cost, x is our speed, and our 3 ordered pairs then would be 10, 28, 20, 21, and 30, 16. Alright, now we're going to determine the 3 equations for our system before we can even use our calculator. And to do that, we're going to substitute it in right up here to y equals ax squared plus bx plus c. Okay? Our first coordinate is the coordinate 10, 28. Remember, x is 10, 28 is a y. So I'm just going to substitute that back in. 28 is going to substitute in for the y. So I have 28 equals, a is not going to change, a is still going to stay a. However, x is now 10. So I have a times 10 squared plus b times 10 plus c. So the only thing I'm substituting in for are the x and the y. So you're plugging in x and y. So one equation here is going to be found by simplifying this. So I get for that equation, let's write this in green, 28 equals 100a plus 10b plus c. Now I'm going to do the same thing. I'm going to repeat that same process, plugging in the next coordinate, 20, 21. This time I have 21 equals a times 20 squared plus b times 20 plus c. Now simplifying this equation, I end up with 21 equals 400a, 20 squared is 400a, plus 20b plus c. And the very last equation is going to come by plugging in 30 and 16. So now I have 16 equals a times 30 squared plus b times 30 plus c. And simplifying this equation, I end up with 16 equals 900a plus 30b plus c. And what I actually did already for the first two lines is I stuck the number out in front, that 28. I put it at the end of the matrix, or the equation, just because I think we're used to seeing the variables first and then equaling a number, because that's how you want to enter it also into your calculator anyhow. So that's 16. I'm going to rewrite that on the other side. Okay. Alright, so this is my matrix that I'm going to enter now into my calculator. So let's define it first. So let's let A equal 100, 10, 1, and 28. Now the reason why I'm using 110, 1, and 28, these are the coefficients in front of the variables, okay? And this is the constant, the 28. Now a lot of people confuse this and they want to write 0 in for the C, but there is a number here, it's a 1, okay? So make sure you put a 1 out there in front of those. So the second line should be 400, 20, 1, and 21, and then 900, 30, 1, and 16. So I'm going to edit that in my calculator. I want you guys to do that too. Okay, you can see here that I actually entered and edited it already. It's now a 3x4 matrix, so it doesn't have enough room to show everything, so if you scroll to the right, you can see the rest of those that data that I entered. So now when I go to my home screen and I hit second quit, I'm going to hit second matrix and RREF, instead of hitting second matrix and finding it all, I'm just going to hit second entry and call up the last thing, and because I've edited A, I won't get the same numbers as last time, but I get this system here. Let's define this. RREF of A is equal to 100.01, 010, negative 1, and 00137. So what this tells me is that A equals 0.01, B equals negative 1, and C equals 37. So there's the answers to those variables. Now our final equation, remember we have an equation that says y equals ax squared plus bx plus c. We just found A, B, and C, so all we need to do is substitute that in. So y is now equal to 0.01 x squared minus 1x plus 37. So this is really sometimes hard for students to interpret the answer. They want to, for some reason, plug 0.01 in for x, but you're not doing that. So make sure that you're looking at what your variables are defined as and what the original equation should look like so that you can plug it in correctly. So that's our equation that relates cost to the speed. Now, the next question here, it says, how much would you spend to drive 65 miles per hour? So 65 miles per hour is a speed, right? So basically what they're telling us is plug in x equals 65 because x was defined way back in the beginning as speed. So now I can plug in 0.01 times 65 squared minus 65, 1 times 65, then plus 37. Now when I do that in my calculator, I want to make sure that I'm entering 0.65 squared, either in parentheses or do that first. So 0.65 squared and times that by 0.01. Oops, I did not mean to put 0.65. Sorry, let's clear that out. 65 squared times 0.01 and then minus 65 plus 37. And we get 14.25. So let's interpret this answer. Remember, this is the cost. Now our cost, if you look at your first data set, was in cents. So y was the cost. And looking at our numbers that they gave us, that was in cents. So this is 14.25 cents, or $0.1425, okay? per mile driven. So that's how much it costs you for driving per mile. Okay, that's the end of the lesson. I know this is a little bit longer than the last few, but we had a lot of stuff to cover. So just to recap, RREF is a pretty easy thing to use. The most important thing, though, is to make sure you understand how to interpret your solution. So go back and replay 6 through 9 if you didn't quite understand any of those. And then number 10, this is probably the most difficult question that we did so far, because we're using this as an application of quadratic models. So first we had to determine what the actual equations were. We did that by plugging in the points that we were given at first. So we had points 10, 28, 20, 21, and 30, 16. So after we defined our variables and after we came up with our ordered pairs, we used the quadratic model that they gave us. This is the quadratic model they gave us, and we just plugged right into there using 10 as our x value, and y was 28. So that's how we got this first line here. We simplified so that we have it in A, B, and C. And we did that, we repeated that 3 times so that we ended up with our matrix. After we plugged in our matrix here, A equaling this matrix here, we row reduced echelon formed it, got this answer, interpreted our solution, and then we had our final equation. Then we used our final equation here in part E to actually find how much you would spend when driving at 65 miles per hour. Okay, that was a long one. Thanks for sticking in there, and come tomorrow to class prepared to answer questions on row reduced echelon form. You'll also have some word problems as well, but you'll get lots of practice with that, and you can ask me any questions that you have tomorrow in class. Nice job. I will see you tomorrow.